remote. Just to give you an update, we've got a session of 3 talks. We've got Tim Lanphier from NVIDIA, Jim Cowney from Intel, and Simon McIntosh-Smith from the University of Bristol. And Tim Lanphier is up first, so take it away, Tim.
So I was joking with Jim earlier on today that sometimes when Intel and I and NVIDIA talk in the same meeting, you may find that actually we're saying the same message, but one of us presents the slides with a green and black color scheme, and the other of us presents the slides with a blue and of the blue color scheme. We didn't clash too much this morning, but perhaps now because we are focusing on the same topic, perhaps you will find more overlap between what we have to say. And that is not unreasonable. Intel and NVIDIA are competitors in this space in the business sense. But on the other hand, we're both trying to solve the same problem, and we both have the same laws of physics to deal with. And so we have similar, perhaps in some ways, similar types of solutions. And in other ways, we're promoting contrasting types of solutions. So you'll hear perhaps 2 different approaches to solving this, essentially the same problem. I'm going to talk a little bit about exascale computing and how we might get there, and some of the things that people want to do with exascale computing. Comprehensive modeling of the Earth at a very fine scale, so you get a rather better looking picture than that one, something much more detailed. Some large scale and detailed modeling of combustion processes. Simulations at the very detailed level of what's going on in cells, at the molecular level, at the genetic level, and plasma physics. We've got this funny image on the side here. I don't know what that's all about. Plasma physics. That's not part of me. And these are the sorts of topics that have been put forward by the large computer centers, in particular places like Oak Ridge Labs in the United States, as the areas that goals that they're trying to solve when they're pressing towards these even larger computing systems. And if we predict, we have this typical viewpoint extrapolation. It's always an extrapolation into the future of where it will take us to get to the exaflop level. This graph shows here the fastest computer in the world. The blue line is the 500th fastest computer in the world, and the green line is the total sum of the flops installed on the top 500 list. And the expectation, or if we make a linear prediction has worked until now. I'm not sure whether linear extrapolation is going to be appropriate for getting us to the exaflop level. Linear on a logarithmic scale, yes. Okay, some sort of exponential prediction. Well, yeah. Whatever prediction it is, it's an extrapolation, and I'm not 100% convinced that we're going to get there, but that's where I'm pretty convinced we're not going to get there. A few years after that, we might eventually get to the exaflop level. I talked a little bit about this issue of power consumption this morning, and Jim also did as well. That one of the things that we're seeing is that the amount of power consumed by these large systems is growing very much. I remember when I started getting into high-performance computing, which was in the early 1990s, the largest machines in the world would have easily fitted on this dais. You could probably have fitted several of them, actually. Now we're talking, then I remember in around about 2000, we were talking about 50 square meters, maybe 100 square meters for the largest machines. And now they're even dramatically bigger than that and using much more power. So we're up in talking about many megawatts of, 80 megawatts of power for the largest machines in the world. And the point I tried to make this morning is that we have to do something intelligent to solve this problem of power. We can no longer rely on the scaling that the scaling laws in the past allowed us to move up to at least to the petaflop scale without too much difficulty. It's not going to work anymore. The laws of physics are now against us, and we can't typically expect for this extrapolation to work for us anymore. And we have to come up with a different sort of solution. It is interesting to note what is consuming all this power. And it's not floating point arithmetic. These days, floating point arithmetic is, to all intents and purposes, free of charge. It will cost you, this is for 28mm silicon technology, it will cost you about 20 picojoules to multiply two numbers together. But once you've multiplied those two numbers together, you perhaps going to want to store them. It'll cost you more than twice as much as that power just to store the numbers. You might want to then move them somewhere else. Moving them across the chip from one side to the other can take you another order of magnitude or more power energy consumption. And that's just inside the chip. If you want to move data off the chip, it gets another order of magnitude worse. And the message here is that now, these days, the floating point arithmetic is free of charge. And what you've got to be concerned about is moving the data and producing data and consuming it consuming data as far as possible in exactly the same place that you produced it. This is the real problem. So what sort of solutions are we looking at? Well, one of the solutions we're looking at is hybrid computing, and all of the major semiconductor manufacturers, NVIDIA, AMD, Intel, have concepts for doing this sort of thing. So you have the more orthodox CPU architecture, which does the stuff it's good at. What is it good at? It's very good at running a modest number of threads where the performance of the individual thread is optimized by lots of techniques, such as out-of-order execution, speculative execution, large caches. So it's very good at less parallel work, and attach it to something else. And different companies have different solutions for this. We have our solution. Jim will perhaps talk about his solution in a minute. But another class of architecture, another style of architecture that is appropriate for highly parallel workloads and perhaps more appropriate for streaming of data with a high bandwidth from memory through to the processor and out again. And indeed, I entirely endorse the remark from John Gustafson this morning, my former colleague John Gustafson, that what's really important here is the performance of the memory and how well the memory works. And as I said, once again, the arithmetic is pretty much a solved problem these days. I do represent the sales division of NVIDIA, unlike Jim, and so I cannot avoid talking about products. It's my duty in life. It's what they pay me to do. These are two of the current generation of products that NVIDIA is shipping. We have a device here on the left-hand side, which has been optimized for single precision 32-bit arithmetic. Actually has two GPUs on it, so one under each of these heat sinks. So a pair of GPUs on a single board. And then we have the sort of flagship, all singing, all dancing, more general purpose device, which has a single large GPU in it. I can foresee there will be a tendency towards having cards with two GPUs on them in the future. And this kind of makes some sort of sense from the angle of high-performance computing, because to a very first approximation, the floating point performance of a device is proportional to its area, and the capacity and bandwidth of the memory system is proportional to the periphery of a device. So if you take the same area of silicon and split it into two pieces, you get more periphery, and so you can get a little improvement in the performance of the memory in comparison with the floating point performance. So two devices, two medium-sized GPUs on a board rather than one large GPU may be the trend in the future. We're still having lots of internal debates on that. There were three things that the designers of this generation of GPU were really looking at. First thing was power efficiency, and we've talked about this ad nauseum. I won't emphasize it again, but if there's one thing that the silicon architects were thinking about when they got up every morning was, how can I make this device deliver the performance more efficiently with less energy? We wanted to enlarge the scope and the breadth of problems that the GPU can solve. So the early GPUs, they were very good at for example, solving one large homogeneous problem, a very large system of matrices, system of equations, for example. But that's not the only class of parallel problem. There are plenty of other classes of parallel problem. For example, you might want to solve simultaneously at the same time several smaller sets of linear equations. So let's try and, with this generation, the architects were interested in enlarging the scope of the scope of applicability. Sorry, and also that was the third point. Second one, make it easier to program. So coming up with some new technologies for programming the devices more easily, such as directive-based programming. Annotate your program with directives in the style of OpenMP, so that codes for the GPU can be generated for you semi-automatically by the compiler. And there was marketing comes up always with interesting names for things. So we can say that the power efficiency was addressed by the new design of the streaming multiprocessor, which, because it's now extra good, gets an X on the end of it, SMX. And HyperQ and dynamic parallelism were a couple of technologies introduced into the GPU to make it easier to program the device and to make it more applicable to different classes of algorithm. And as a consequence, I can still use this slide for another few days until the top 500 list comes out, and then I'll have to hand the baton over. But at least for the next couple of days, I'm going to continue using this slide of having the largest computer in the world, which was installed in Oak Ridge Labs, with 18,500 Tesla GPUs in it. And I'm glad to say now that actually it has been formally accepted. I think there may be some paperwork still involved, but everyone's agreed it does work now. It took a little longer than had been expected. But the point is, this is not simply a stunt machine for running LinPack. This was a machine that was driven by the demands of the scientists at Oak Ridge, and they set us the challenge of dealing with these, identified six key applications that were running on that machine, which you can see do address some of these challenges of the Exascale demands. Combustion will be one of them, climate modeling, material science, looking at, these are the sorts of challenges that are going to be key for scientific advance in the next few years. And the good news is that we did, in fact, deliver value with these 18,000 GPUs. They do deliver value beyond the LinPack test. And so you can see here that we're getting up to an order of magnitude speed up of the applications when accelerated by the GPU. So in the remaining few minutes, let me have a quick look into the future and talk about some of the directions that the NVIDIA GPU, the NVIDIA technology might be going. So the first point is that the individual processor is not getting any faster. We've seen this is a pure fact of life. What we're getting is more parallel, wider processors rather than the individual processor getting dramatically faster. And so the programmer has to deal with the problem of how do we exploit this parallelism. And I'm afraid that for the application developer, you don't really have a choice. Today is the time you have to start facing up to this and start dealing with it. Locality, data locality, I've talked about earlier on the fact that consuming the data where it's produced is the key point. Try to avoid as far as possible moving data around. So we used to calculate data and store it. Recalculation is a much easier thing to do now than to try and fetch data from somewhere else. So we have this, but we do still have, these are not easy tasks for the programmers to deal with, and so we do need to help them in coding in these sorts of ways. And so working on the technology to do so is one of the tasks that's going to be key, I think, for the next few years. I do recall hearing Professor Mike Payne from Cambridge talking about this issue a few weeks ago. his remark was something like, well, we're investing all this money in hardware in the UK, and we're spending absolutely no money at all on developing the applications that are going to run on these machines. We're missing out a lot here by the country not investing in the application development skills and abilities, and just investing in large pieces of hardware. What might we expect in the future? Well, more integration. We're getting more and more transistors. Thanks to Gordon Moore, we just get more and more transistors, so we can put more and more onto the chip. So stuff will be integrated further into the devices. We have to think more. The data locality question is just going to get probably more exacerbated, so keep working on this. We want to try and reduce the overheads of moving data around. So one of the things that NVIDIA research does look at is how to improve the efficiency of moving data around inside chips and how to improve the energy consumption of moving data off chip into somewhere else. We have research teams working on these topics. And I think the other, perhaps a key economic issue, and we'd like to think that we are technologists, but actually, well, we are technologists, but actually our lives and what we do is largely driven by the practical economics of what can be manufactured and what companies can make a profit out of. And what companies can make profits out of quite easily is consumer-grade products, consumer-grade graphics cards, and devices for mobile, processors for mobile devices like tablets and mobile phones. These are products that get sold by the million, tens of millions per year, billions of dollars of income to NVIDIA. And when you have that sort of revenue stream coming in, then you can start doing the interesting stuff like the high-performance computing as an adjunct. So exploiting the technology of these large-scale consumer devices is likely to be a key issue for the future. This is where we will expect to go in the next few years. I'm glad to say that the CEO has revealed the code name for the next GPU. I've known what it has been for some time, but I didn't want to be the person who leaked it out to the company, so I had to be very careful when I was talking and keep on saying Maxwell +1 rather than Volta. We codename our products after famous scientists. And here's some of the things here are some of the key features that have been added in each generation of GPU. So general purpose programmability back here, 64-bit arithmetic, dynamic parallelism, so helping to program the GPU by enlarging the scope of applicable algorithms, unified virtual memory. So these GPUs and CPUs have disjoint memory spaces. It's a bit of a pain for the programmer to have to explicitly move data around. So if you can help him by having some automatic movement of data between CPU and GPU, that would be a good thing to do. And then the technology of the memory is likely to have improved by, number doesn't seem to be there, but it looks like it's going to be about 2016 or so. By that time, we expect to see stacked DRAMs available. So we'll be moving memory onto the package, packaged up with the GPU rather than having a separate package of memory with all the attendant overheads of moving data off package into another chip. And so this will certainly help with the bandwidth and the energy consumption issues of the memory system. And so in conclusion, we believe the future of HPC is green, happens to chime very well with our corporate color. The future is green. Work should be done by processing cores that are designed for power efficiency. We, of course, believe that the GPU is a good architecture to do that. You might hear a different view in a couple of minutes, but there we go. The healthy competition in this market tends to, we hope, will build the size of the provide a slice of a bigger cake for both of us. Align with consumer technology and focus on the integration of more and more components into the devices as time evolves and more transistors become available to us. And this is the way it's going to be in the future. The application developer is going to have to face the way this is the future. This is the reality of the future. The future is very parallel, possibly heterogeneous. You know, Jim said something different this morning. We believe it's going to be heterogeneous, and this we believe is the reality that the application programmer is now going to have to work with in the future. So that concludes my presentation. Thank you.
Great, thank you, Tim.